Alright, in this chapter we are going to study sets and functions. But before that, we need to define some language to talk about sets and functions, and that is formal logic. First of all, we define the term definition, proposition. So proposition is a statement which is either true or false. When it's true, we usually use this symbol. It looks like T, standing true, and when it's false, we use this symbol, which is kind of opposite of T, upside down T. Okay. So, for example, Dr. Akira teaches at university, teaches at UBD, for example. Say, Dr. Akira teaches at UBD. This is a statement which can be either true or false. So this is a proposition. And another example, any even natural numbers greater than or equal to 4 is equal to a sum of 2 primes. So let's say if n is even number greater than or equal to 4, that is 4, 6, 8, 10, 12, and so on. So any natural numbers that are even and greater than or equal to 4 can be expressed as sum of 2 primes. So p plus q, where p and q are primes. So this is a statement that can be either true or false. So this is a proposition. Okay, but we don't know if it's true or false, but it should be either true or false. Okay. Now we define a few operations on propositions. The first operation is called conjunction. So it sounds difficult, but what it means is really simple. It means logical and. Okay, so let's say P and Q are propositions. So that means P and Q are statements which can be either true or false. Okay, P is something like it is raining today, and Q is something like the road is wet. So these statements are propositions, and we define conjunction P and Q. So we use this symbol to state and the definition is this. We define this operation in terms of the truth table. Okay, truth table, which is something like this. Let's say P, Q, and P and Q. Okay, when P is true and Q is true, then P and Q is defined to be true. And when P is true and Q is false, then P and Q is defined to be false. When P is false and Q is true, P and Q is defined to be false. When P is false and Q is false, then P and Q is defined to be false. So this is the definition. This table is the definition of conjunction or logical AND operator. Okay. Next, we define another operator called disjunction, which really means logical or. Okay, so again, if P and Q are propositions, then we define operator P or Q. And again, we define this operator in terms of truth table. P, Q, and P or Q. So when P is true and Q is true, P or Q is defined to be true. And P is true, Q is true, then P or Q is defined to be true. When P is false, Q is true, and P or Q is defined to be true. And when both are false, then P or Q is false. So this is the definition of conjunction. So, this makes intuitive sense, right? If either is true, both or either is true, then these are all true. And if both are false, then P or Q is also false. The next operation is negation. So this means logical not. So if P is a proposition, then we define not P. Okay, so this means not P. We define this operation by this truth table. P is either true or false. So when P is true, not P is false, right? When P is false, not P is true. So it's just opposite of P. Easy. Now we have defined three operators: logical AND or conjunction, or logical OR, that is disjunction, or logical NOT or negation. So if P and Q are both propositions, then this P and Q is also a proposition, and P or Q is also a proposition, and not P is also a proposition. So, proposition can be made more complex. Let's see a few examples. As usual, let's say P and Q are propositions. Then what is the truth value of not P or Q? Okay. By the way, this means this, not P or Q. And by this, we do not mean P or not P or Q. So this is wrong. This is wrong. This is correct. Okay. So that means this not negation operator binds to a proposition more strongly than disjunction or conjunction. Okay. So what's the truth value of this? So we can derive the values of this from the truth table, like this. Let's see. So P, Q. So these can be either true, 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 false, false, true, and false, false. First of all, we derive the values of not P. Okay, not P. And just looking at this column, we can just swap the truth values. So if true, then this is false. If this is true, this is false. This is false, this is true. False, true. Okay, then not P or Q. So look at this. So we combine this Q and this not P. So if true, false, then not P or Q should be true, because one of them is true, right? That's the definition of OR, this one. And false, false, then this should be false. True, true, this should be true. And false, true, this should be true. So these are the values of not P or Q. So in this way, you can derive the truth values of any complex propositions. Okay, now you know three operations: conjunction, and disjunction, and negation. And these three operations are actually sufficient for mostly all of propositional logic. But for convenience, we introduce yet another operation called implication. Okay, implication, which is written as P implies Q. Okay, but actually this is not something new really. It is just a shorthand for a complex operation. Combination of operations. We will see later. And so the definition is, if we have P and Q, is true, true, then P implies Q is true, right? And if P is true and Q is false, then P implies Q is false. If P is true, then Q is true. So this is what this intuitively means. So when P is true and Q is false, then this implication as a whole should be false, right? And if P is false and Q is true, guess what happens? This we define to be true. If the premise, this assumption is wrong, if it's false, then anything can be true. So if this is false, then whether, even if Q is true, even if P is false, this is defined to be true. And if both P and Q are false, then this is again true. So this may sound strange, but if the premise assumption is wrong, then anything can happen. Anything can be derived. So this can be all true. Okay, so that's this is the definition of logical implications. Okay, so basically this is, if P is true, then Q is true, or P implies Q. So that's what this means. Now, related to this, we define a set of related notions. So let's say we have this proposition, P implies Q. So this is again a proposition. Okay, then with respect to this proposition, we can also consider Q implies P. This is called converse. Okay, so this is converse of P implies Q. Okay, and we can also consider not P implies not Q. This is called inverse of P implies Q. Okay, and also we can consider not Q implies not P, and this is called contrapositive of P implies Q. Okay. By the way, when we write not P implies not Q like this means this is stronger. Okay. This does not mean not P implies not Q. So this is wrong. Okay. And same for this. Okay. So we have the definition of implication like this. And we know all the definitions of negations. Negation. So you should be able to derive the truth values of this. Okay. Let's try this one first. So what's the truth value of Q implies P? Let's see. P, Q implies P. So maybe to compare with the original definition, we should swap this one and this one, but let's write. If both are true, if Q is true and P is true, then Q implies P should be true. If P is true and Q is false, then this is Q is false and P is true, so this should be true. And if P is true and Q is false, then Q is false, the premise is false, then whatever the value of P, the implication is true. And if both are false, oh wait a minute, oh no, this is both are false, sorry, I think this is true, and let's see, okay, this is true. In that case, so Q is true but P is false, so in this case this implication should be false. Okay, compare this with the original implication. P implies Q. So this should be true, and this is false, and this is true, and this is true. So if you compare Q implies P with P implies Q, then this is same, but this is different. And this is different. This is same. So this means even if P implies Q is true, that is this case and this case, Q implies P may not be true. So that is, let's see, this case. So this is true, but this is false. And also this is true, but this is false. So P implies Q does not imply, it can be confusing. Even if P implies Q, it does not mean Q implies P. So the converse does not always hold. Okay. In a similar manner, you can show that inverse is not equivalent to the original proposition, implication. But if you compare, let's see, P, Q, we want to derive the truth values of Q, not Q implies not P. So to do so, first we derive not P and not Q. Okay, so true, true, that's false, and false. So false is this part, so this should be true, right? And if this is true and false, then that's false and true. So this part is true and this part is false, so this should be false. Okay, and false, true, that's true, false. So this premise is false, so it should be true. And both false and false, true and true. So true and true is true, right? Now compare this. We don't have. Compare this one with the original proposition. This one. That's true, false, true, true. Okay? And this is true, false, true, true. So that means P implies Q. This is equivalent to not Q implies not P. Okay? So contrapositive of an implication is the same as the original implication. Okay, so they have the same truth values. This one and P implies Q. This has true, false, true, true. Right? So this gives you a way to prove things in an interesting way. So this is the basis of proving by contradiction. Okay, suppose, so not Q. So if you want to prove some theorem that is of this form, if something holds, then something else holds. To prove that, you first deny the conclusion. So that is the denial, negation of the conclusion. Then you derive the negation of the assumption. So that is the contradiction. Okay, contradiction to the original assumption, right? P and not P doesn't hold together at the same time. So this is the basis of proof by contradiction. Okay. Previously I said this implication operator is not something new. In fact, this is equivalent to this proposition, not P or Q. Okay, so to see this, try to write the truth table. So PQ, true, 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 false, false, true, false, false. This case is true and false, true, true. And if you try to derive the truth values of this, you will find it's the same as P implies Q. You should check this. Okay, this is an exercise. Therefore, this is just a shorthand notation for this proposition. Now we move on to defining sets. So what is a set? So it's actually a very deep question, and it's not trivial at all. I mean, this question has a long history of confusion. But here, we don't dig into the details of the definitions of set. We simply define a set as a collection of distinct objects. Okay, for example, we write something like this. This is a set of three objects, A, B, and C. And these objects are distinct in that we can distinguish between any of these elements from other elements, right? A is different from B and C, and B is different from A and C, and so on. Okay, so this distinction is very important. For example, why is this important? For example, if we have something like this, this is not a set because this A and this A and this A, we cannot distinguish them. Okay, so this is actually a multiset, which is important for database theory, but in mathematics we usually don't deal with this kind of multisets. But instead we disregard the redundancy, so this A and this A, this A, they are all the same. So this multiset, we regard this as equivalent to this set. So we just ignore the redundancy. Okay, and each object is called an element. Okay, and we may name each set by some symbol. For example, S is a set consisting of three elements A, B, and C, right? And if we have an element, we can write this as this. Okay, A belongs to S, or we say A is an element of S, right? Or X is an element of S, and so on. In this case, if this S is this set, then this X should be one of A, B, or C. And if X does not belong to this set, we write it does not belong to S. Okay. And we also define subsets. Let's say S is a set, and also A is a set. Okay, if X is an element of S, so if this statement, so this is a proposition, right? It's either true or false. If this implies X belongs to S, so this is another proposition, then A is a subset of S, and we write A is a subset of S. Okay, sometimes we write A is a subset of S like this. So we might write this straight line here, but okay. So here's one lemma. The relation of subset is transitive. Transitive. So this means if A is a subset of B and B is a subset of C, then A is a subset of C. Okay, so subset means, okay, let's go back to the definition of subset. x is an element of A, this proposition implies x is an element of S. So this means every element of A is an element of S. Okay? So that means the entire A is completely contained within S. So this is the meaning of subset. So this relationship is transitive, meaning if A is a subset of B and B is a subset of S, then A is automatically a subset of C. Okay, so this relationship is transitive. So that this is what this means. So intuitively, this makes sense. Okay, A is a subset of B, means A is completely contained within B. But we also have this condition. B is a subset of C. So B is completely contained within C. So if this is the case, then A is completely contained within C. So this holds, right? So this is the intuitive proof of this lemma. Okay, but let us prove this more formally. Okay, so what's given here are this condition and this condition. Okay, so from these two conditions, we derive this result. A is a subset of C. So suppose A is a subset of B. This means if X is an element of A, then X is an element of B, right? This is the definition of subset. Okay, but since B is a subset of C by this given assumption, this implies X is an element of B implies X is an element of C. So that means if X is an element of A, then after all, X is an element of C. Therefore, X is an element of A implies X is an element of C. That is A is a subset of C. So that is the proof of this lemma. Okay. Let us review some of the famous, well-known sets. First of all, you should know the set of natural numbers. And we don't exactly define what natural numbers are. We just assume you already know this. So natural numbers are numbers that start from 1 and 2, 3, 4, and so on. So there are infinitely many elements. Okay? It's easy. Well, some mathematicians prefer to include 0 as a natural number, but here we don't adopt that convention. In our natural number, in our set of natural numbers, we do not include 0. Okay, and the second set is, of course, integers. So this is a natural number is denoted by this n, it's bold n, and integers are denoted by this z. Okay, so this includes negative numbers like -2, -1, and also 0, 1, 2, and so on. And we don't exactly define integers, but we just assume you already know what they are. Okay, and if we already have the set of integers, the set of natural numbers can be expressed as this. It's a natural number. The set of natural number is actually a subset written like this. So it's a set of x, where x is an integer and x is positive. Okay, so in this way we can redefine the set of natural numbers as a subset of integers. Okay, so the set of natural numbers is a subset of the set of integers. And next, of course, rational numbers. Let's write the set of rational numbers by Q. Q stands for, I think, quotient. So this is like A over B, where A and B are elements of Z. That means A and B are integers, and B is not 0. Okay, so this is a kind of definition of rational numbers. And from this definition, you can see that the set of integers is a subset of the set of rational numbers. Okay? And we also know that 0.5 is equal to 1 over 2, which is also equal to, for example, let's say 5 over 10, and so on. So actually this set is quite redundant, right? So according to this definition, this set should contain both 1/2 and 5 over 10, but they are both equal to 0.5. So this is redundant, so we just disregard this redundancy and only consider distinct elements of this set. Actually, this operation of ignoring redundancy requires some tricks, but we don't talk about it right now. Okay, and the next set is the set of real numbers. How to define real numbers is far from trivial, but we just assume you already know what real numbers are. So real numbers cannot be expressed as a countable set. Well, countable, we haven't defined it yet, but anyway. So real number is a number that includes both rational and irrational numbers. Okay. So we write the set of real numbers by this symbol. And this includes something like square root of 2, which is irrational. So 1, 4, 人よ人よに人みころ and so on. Okay. And yeah, defining real numbers is really, really hard, but that is a subject of real analysis, I guess. Of course, the set of rational numbers is a subset of real numbers. Okay. Here, let us introduce one axiom regarding the set of real numbers. Okay, let's call it axiom. Axiom is something that we regard is a statement we regard as true. Okay, we accept as true, and this is called Archimedes Principle. Archimedes principle. For any arbitrary for any positive real number, number A and any real number B, there exists a natural number let's call it n, so natural number, such that a n is greater than b. Okay, so this is not a theorem. Okay, this is an axiom, so we accept this as true at this point. Yeah, well, actually, if we accept some other axioms, this may be derived as a theorem, but here we accept this as an axiom. Okay, so a is a positive real number and b is any real number. Then, so a and b are any numbers, okay, as long as a is positive. Then we can pick some natural number n such that a times n is greater than b. Okay, what does this mean? What does this mean? So for example, let's say a is 0.01 and b is -1. Okay, so any natural number can actually satisfy this an times b, right? So 0.01 times 1, for example, is of course greater than negative number, right? So this is trivial. Let's say then a is 0.01 and b is, let's say, 100. Can we choose any natural number satisfying this? Actually, we can, yes. For example, let's say n is 100, let's say 1000. Then a times n is 0.01 times 1000, which is 10. Oh wait, no, it's not. Okay, 100,000. Maybe 200,000. 200,000. Then that is 200. And is it? Yeah, 200, which is greater than 100, which is b, right? So this looks reasonable. Okay. Now, using this fact, let us prove that this lemma, square root of 2 is irrational. So how can we prove this? Square root of 2 is irrational. Irrational means it's not rational, right? So we prove by contradiction. So contradiction means if we assume square root of 2 is rational, then there is contradiction. Okay? So assume square root of 2 is a rational number. So if it's a rational number, then it can be expressed as a ratio of integers, right? M and n are integers, and n is not 0. right? And for simplicity, we assume that m and n have no common divisor. Okay, so it is already reduced. Then, if we square both sides, then we have 2 is equal to m squared over n squared. So this means, so this implies m squared is 2n squared. Okay, so this means m squared is a multiple of 2. So this means m squared is an even number. Okay, so this is an even number. So this implies m itself is even. Why? If m is not even, then it should be odd, right? So suppose m is odd, then we can express m as 2 times some integer plus 1. So it's an odd number, right? So k is an integer, where k is an integer. So if we square this, then we have 2k plus 1 squared, which is, let's see, 4k squared plus 4k plus 1, which is, let's write in this way, 4k squared plus k plus 1. But this is even number. 4 is an even number. 4 times something is an even number, plus 1. So this is not even. So this is odd. So, but we are saying m squared should be even. So this is a contradiction. So therefore, m cannot be odd. M itself must be even. Okay? So that means m is expressed as 2 times some integer. Okay? But we have this m squared equal to 2n squared. So if we substitute m by 2k, we have 4k squared is equal to 2n squared. But we can divide by 2 both sides, and we have 2k squared and n squared. Okay? Then, by the same argument as before, we can derive that n is even. Okay? So that means n is expressed as 2 times something. Now, this is a contradiction. Why? Because m is a multiple of 2 and n is a multiple of 2. But in the beginning, we assumed that this is already reduced. So that means they didn't have common divisor. But we have common divisor, that is 2. So this is a contradiction. Therefore, our original assumption was wrong, and that original assumption was square root of 2 is a rational number. So the proof is done. Now let us prove one of the most important properties of rational numbers and real numbers, that is denseness. So that is this set, the set of real numbers, rational numbers and real numbers are dense. What this means is the following. This is actually a theorem. 1.1. And a and b are real numbers such that a is less than b. Okay, then there exist a rational number such that x is between a and b, and a real number y such that y is between a and b. Okay, so as long as a is less than b, we can always find a rational number between them and a real number between them. Okay, so even if a and b are very, very close, we can always find some numbers between them. Okay, let's prove this. So we can choose a natural number such that 1 is less than n times b minus a because of Archimedes principle. Right? 1 is a real number, and b minus a is a positive real number because a is less than b. So we can choose a natural number like this. Okay, and so this means 1 over n is less than b minus a. Okay, and next we choose an integer. Actually, the least integer. Least integer such that bn is less than or equal to z. Okay. B times n is some number, so we can always find the minimum or the least integer that satisfies this inequality. Okay, so this means b is less than or equal to z minus divided by n. Okay, since this z is the least such number, that means z minus 1 is less than bn, right? Because this z is the least integer that satisfies this. So if you subtract 1 from this z minus 1 should be less than bn, right? Okay, so this means z minus 1 over n is less than b. So we have this and we have this. So now we have a is equal to b minus a, right? So it's just an identity. And this part, we have this. So this is less than b minus 1 over n. Because of this negative sign, this inequality is swapped. Now, this is less than, and this is less than. And because of this, b is less than or equal to z over n, we have this is less than or equal to z over n minus 1 over n. Right, so this part corresponds to this part. And we have z minus 1 over n, but now we have this inequality. So that is less than b. Okay, so that means if we define x as z minus 1 over n, which is a rational number because z is an integer, and 1 is an integer, and n is an integer. So this x is a rational number. Then this x is between a and b, right? So this is this. So we have proved half the theorem. So this part is proved. Now we need to find a real number. Actually, it's not real number, it's an irrational number. Okay, it's not, let's see, it's irrational number, so it's irrational. Okay, so now try to find an irrational number. Let's try to define, choose a integer m, a natural number m, such that square root of 2 is less than m b minus x. So this x is this x, okay? So b is a real number and x is a rational number and m is an integer. So this is again from Archimedes Principle. We can choose such an integer, such a natural number. Okay, and then define. So this is. So from this we have square root of 2 over m is less than b minus x. Okay, now let's define y as x plus square root of 2 over m. Then this is irrational number. Right? X is a rational number, and as we have proved, square root of 2 is irrational and m is rational, of course. So it follows that y should be also irrational. Otherwise, if you rearrange this, otherwise we have square root of 2 is equal to m times y minus x. Okay, if y is rational, then y minus x should be rational, and m times y minus x should be rational. So that means square root of 2 is rational, which is a contradiction. So y must be irrational. Okay. Then we want to show that this y is between a and b. And okay, so x is greater than x plus square root of 2m, which is y. And this part, from the way we have chosen this m, we have x plus b minus x, which is b. Right? Let's see here. So square root of root 2 divided by m is less than b minus x. So we have this inequality, and we have, therefore we have x is less than y, which is less than b. But we have shown that x is greater than a. So that means y is between a and b. So the proof is done. Next set is the set of complex numbers, which we denote by this symbol, C. Okay, and of course, complex number is based on the imaginary unit. Which is the square root of -1. Right, so this is I. And the set of complex number is formally defined as this. So A and B are real numbers. Okay. And we will see a different definition of complex numbers in the next chapter, which I think is more interesting. But here we just leave the definition as this. And one of the most important, maybe it is the most important set is the empty set. Which is the set that contains nothing. Okay, so which we denote the empty set as this, 0 with slash. Okay, which is nothing. Okay, since it's nothing, it is the only empty set. Okay, empty set is unique. Okay, if there are two empty sets, they must be equal, right? And what's important is to note is that empty set is a subset of any sets. Okay, if A is a set, if A is a set, any set, then empty set is a subset of that set. Okay. And for example, empty set is a subset of the set of real numbers, and so on. Now that we know some of the well-known concrete sets, let's go back to the general properties of sets. And we introduce some set operations. And the first of them is called union. Okay. So let's say A and B are sets. Then the union of A and B is written as this and defined as this. So that is a set of elements that belong to A or that belong to B. Okay, so this is the definition of the union. Okay, here we use the logical operation here. That's disjunction, right? And X belongs to A and X belongs to B. They are propositions, right? So this is a proposition and this is a proposition. So we can combine them by logical or disjunction. So this part is another proposition that defines each element of the union between A and B. Okay, here's an example. Let's say A is a set of three numbers, 1, 2, 3, and B is a set of three numbers, 1, 3, 5. Then A union B, or we say A cup B. Now this looks like a cup, right? So A cup B is 1 and 2 and 3 and 5. So let's check the definition here. 1 belongs to A and B, so it satisfies this proposition, right? And 2 belongs to A but not B, but it's okay because we are using OR here, so this is okay. And 3 belongs to both A and B, so it satisfies this. And 5 belongs to B, not A, but it's okay. So every element of A cup B belongs to either A or B, or maybe both. Next, we define intersection. Again, let's say A and B are sets, any sets. Then the intersection between A and B is written as a cap B. Okay, this is called cap because it looks like a cap, right? On your hat, it's like a hat. A cap B is defined as the set of elements that satisfy this proposition. X belongs to A and X belongs to B. Okay, here we use logical AND, so it's a conjunction. So that means each element X must satisfy both this proposition and this proposition. X belongs to A and X belongs to B. Okay. And let's see an example. Let's use the old example. 1, 2, 3, and B is 1, 3, 5. Then A cap B is all the elements that belong to both A and B. So that is 1 and 3. So this is the intersection of A and B. Okay. And let's define the notion of disjoint sets. Disjoint sets. So again, let's say A and B are sets. Then we say A and B are disjoint. A and B are disjoint if A cap B is empty. Actually, if and only if. So let's say. So these are equivalent. I mean, it's the definition. So in the previous example, in this case, if A is 1, 2, 3 and B is 1, 3, 5, then the intersection is not empty. So this A and this B, they are not disjoint. Okay. Now let us prove a seemingly trivial lemma about commutativity. So that says union and intersection are commutative. So what does this mean, commutative? It means if A and B are sets, then A cup B is equal to B cup A. And similarly, A cap B is equal to B cap A. So that means when you apply this operation of union or intersection, you don't have to care about the order of the sets. A union B is equal to B union A. A intersection B is equal to B intersection A. So this is just like, it seems trivial, but we need to prove this because from the definition, it is not immediate, right? So, but anyway, this commutativity seems trivial because you've used to the commutativity of numbers, right? So if x and y are, let's say, real numbers, then we always have x plus y is equal to y plus x, or x times y is equal to y times x. So it's like this commutativity. Anyway, let's try to prove this. Okay, so to prove this, if we want to prove two sets are equal, okay, so this is a set and this is a set. If we want to prove two sets are equal, what we do is this. First, assume x belongs to A cup B. Then, from this, we prove x belongs to B cup A. Okay, so if this can be proved, then it means A cup B is a subset of B cup A. Okay, so this is the first step. And the next step is assume A belongs to B cup A. Then from this, prove that X also belongs to A cup B. So this proves that A cup B, this proves B cup A is a subset of A cup B because every element of B cup A belongs to A cup. Every element of B cup A belongs to A cup B. So this means B cup A is a subset of A cup B. Okay, if these two things are proved, then that means A cup B is equal to B cup A. Okay, so this is the strategy of our proof. So let's prove this lemma according to this strategy. So suppose x belongs to A cup B. Then, by the definition of the union, that means this proposition holds. X belongs to A or X belongs to B. Right? So suppose this, then this. Okay, but of course, this logical statement doesn't depend on the order. So this means X belongs to B or X belongs to A. So we are saying the same thing in different ways. Okay, but this means this statement implies that X belongs to B cup A according to the definition of B cup A, right? B cup A is a set of elements that belong to B or A, right? So from here we derived this last statement. So this means A cup B is a subset of B cup A. So we can repeat the same thing starting from here. So assume X belongs to B cup A, then it means X belongs to B or X belongs to A. And this is the same thing as X belongs to A or X belongs to B, which means X belongs to A cup B. So therefore, by going from here to here, we prove the opposite subset relation. So therefore, A cup B is equal to B cup A. Okay? So next, we want to prove A cap B is equal to B cap A. But the way we prove this is very similar to the previous case, so I leave it as an exercise. Okay, that's it. The next lemma is about associativity. Okay, what does it mean, associativity? And we want to say union and intersection are associative. Okay, so this means if we have A, B, C sets, A cup B cup C is equal to A cup B cup C. Okay, so this means first we take the union between B and C, then take the union between A and B cup C. So this is associativity, means that this is equal to this. First take A cup B, then from with this we take the union of C. So this means the order we apply the union doesn't matter. So this comes first, then this comes, which is equal to this comes first and this comes. Okay, so this means associate. Union is associative. And the same thing holds for intersection. A cap B cap C is equal to A cap B cap C. Okay, so this means union is associative, and this means intersection is associative. Okay. Because of these properties, we can simply write something like this. A union, for this, we can write A union B union C. So A cup B cup C without parentheses, because we don't have to worry about the order, which union should come first. Either can come first, and we get the same result. And same for the intersection. Okay. And again, this is a very similar property as numbers. So suppose A and B and C are real numbers. We always have A plus B plus C is equal to A plus B plus C. And A times B times C is equal to A times B times C. So the which addition comes first doesn't matter. Therefore, that's why we can write either of these as just A plus B plus C, or A times B times C without any parentheses or brackets, right? So this is a very similar property. And the proof of this is very similar to the previous proof. So first we assume, first we assume X belongs to this. Then from this, we prove that X belongs to this. And do the same thing in the opposite direction. Then we can say that these two sets are actually equal. And same for intersection. Okay. Well, we have two operations so far about between combining two sets. One is union and the other is intersection. In ordinary numbers, we also have two operations called addition and multiplication. And they are kind of similar. And there is a law called distributive law that combines addition and multiplication in case of numbers. And we have similar laws for sets. So here's another lemma called distributive laws. Distributive laws. So again, we have A, B, C that are sets. Now we have A cap parenthesis B cap C is equal to A cap A cap B cap A cap C. Okay, so this cap operation distributes over union. Okay, so this is cap, this is cap. So A cap B cap A cap C. And similarly, we have A cap B cap C and A cap B cap A cap C. Okay. In many cases, cap operation, so union, is similar to addition of numbers, and cap or intersection operation is similar to multiplication of numbers, but they are not exactly similar. Okay. For example, if you consider cap as multiplication and cap as addition, this first one translates as something like this. Times B plus C, which is A times B plus A times C. But the second one would translate as A plus B times C, which is not equal to A plus B times A plus C. So, this is the second equation here is very specific to the operation of sets. Okay? So don't just rely on the analogy. We have to prove this based on the definitions of union and intersection. Okay. Now let's prove this. As usual, if we want to prove two sets are equal, then first assume one element, each element belonging to one set also belongs to the other set, and vice versa. Okay, so first suppose x, suppose x belongs to A cap B cap C. Okay, from the definition of, first we consider A and B cap C, okay, these two sets. Then according to the definition of intersection, this means x belongs to A and x belongs to B cap C, right? And now consider this part. This means x belongs to A and x belongs to B, or x belongs to C. right? And then this means, well, actually this we need to prove the distributive law for logical operations, but we proceed intuitively here. So this and this or this means x belongs to A and x belongs to B, or x belongs to A and x belongs to C. Can you see this and this are equivalent? They should mean the same thing, right? So now this means x. Now consider this part first. This means x belongs to A cap B according to the definition of intersection. Or the second part, this means x belongs to A cap C. Now consider everything here. Then according to the definition of union, this means x belongs to A cap B union A cap C. So therefore, this set is a subset of this set, right? So from this we prove that this is a subset of A cap B cap A cap C. Now conversely, suppose x belongs to this, A cap B union A cap C. Then going backwards this argument, we can prove that this one is a subset of A cap B cap C. Therefore these two sets are equal. Okay, and you can prove the second distributive law, this one, in a similar manner, and that will be an exercise. The next lemma is about empty set. Suppose A is any set, then we have A union empty set is A, and A intersection empty set is empty set. So I don't give a proof here. Try to prove it, but you should think hard what this means. X belongs to empty set. What does it mean? Now, as usual, if you want to prove this, first assume X belongs to A union empty set, then prove X also belongs to A, and vice versa, and similar for this one. Okay, so especially in the second case, you need to think about what this really means. Empty set is a set which contains no elements. So try it. Next, we define set difference. Definition of set difference. And suppose A and B are sets. Okay, and the set difference is written A minus B. So minus is not this minus, but we write as backslash. So A set minus B is defined as the set of elements which belong to A and not belong to B. Okay, so intuitively if we have two sets like this, A and B, this set difference means those part that is the part belonging to A but not B. So it means this part. Okay. So that means you first take A and remove the elements that belong to B. Okay, so remove this element. And that is the set difference. And related to this, let me give a small lemma. And that is A minus B and B minus A, they are disjoint. So this cap this B minus A is empty. So there are no common elements of these two. So intuitively speaking, so okay, so this part, this part is A minus B, and let's see, this part is B minus A. So as you can see, these two sets do not have anything in common, right? So that's what this lemma means. But you should try to prove this based on the definitions. Now let us introduce the notion of the universal set. Universal set, or simply universe. Okay, a universal set is the set of everything we want to consider, so to speak. Actually, we cannot define the set of literally everything because that will lead to some contradiction, very serious contradiction. So there, a set must satisfy a certain set of axioms, but we are not digging into the details of this. But anyway, just suppose a universal set is a set of everything we can rationally imagine or want to consider, as long as it is consistent with the whole entire mathematics. Okay, now using the notion of the universal set, we define set complement. So that is, suppose U is a universal set. Universal set. And A is a set. So if we consider a universal set, any set is a subset of the universal set. Okay, so it's a universal set is a universe, so that contains everything. So A is a subset of U. Okay, it must be, whatever this A is. Okay, and the complement of A is defined as A prime, which is the set difference U set minus A. Okay, so this is the definition of the set complement. So so intuitively speaking, suppose we have this universe. Okay, so this is the universal set, and we have a set A. So this A complement, A prime, is u minus a, so that means it is this part. So everything outside a. Okay. So this is the a complement. Okay, so this part is a prime. And by this definition, it is immediate. The set complement of a complement is the original set. Okay, so if you take the complement of a prime, then it must be equal to a, right? So this one we just abbreviate to prime. So it means the complement of a complement. Okay. Please try to prove this. And for the sake of explanation, if we go back to the definition of the set difference, the set complement is defined as this. X belongs to U, and X does not belong to A. Okay. Now, let us prove a few more lemmas that involve set complements. Okay, another lemma. U means universal, universe. Okay, and A is any set. Then A cup A prime, complement of A, is equal to U. And A cap, A complement, is empty. Okay. This is almost trivial, right? And this is also trivial because any element, if X belongs to A, then it cannot belong to A prime by definition, and vice versa. So there should be no common elements between A and A prime, so they must be disjoint. Okay, but you should try to prove this more formally. And another important lemma is called, let's say it's a theorem. It's De Morgan's law. Okay, as usual, A and B are sets. Then the complement of A cap B is equal to A complement cap B complement. And A cap B, its complement is equal to A complement cap B complement. Okay. Again, by using Venn diagram, the first one, suppose we have, this is U and this is A and B. So A union B is this part, right? So its complement is everything else outside A or B. Okay. So this part, yellow part, is A union B complement. And the right hand side, so A complement is, okay, this is A, this is B. A complement is everything outside A. Okay, and B complement is everything outside B. Okay, and their intersection is where? That is, I don't have any colors, so that means that means this green part, right? So everything in between this part. So this red shadow is equal to this yellow part. So that's what this means, and you can visualize the second equation in a similar manner. But you should try to prove this based on the definitions, and that's an exercise. We can also define sets of sets, or a set that contains other sets. For example, suppose T is a set containing this 123 and 1 2 3 1 2 3. Okay, this is a set, and the first element, this one, is a set that contains 1 and 2, and the second element is another set that contains one element, that is 123, and the third element is again a set that contains three elements 1 2 and 3, and the fourth element is not a set, it's just a number 1, and another element is not a set, it's a number, and the last element is again a number. So we can mix basic elements and sets as elements of a set. Another example, suppose S is a set consisting of 0 and 1. And for example, we can define something called power set, which is the set of all subsets of S. Okay, power set of S is the set of all subsets of S, and that is all subsets of this is what? First, empty set, and the set consisting of 0, and the set consisting of 1, and the set consisting of S itself, that is the set of 0 and 1. Okay, so in this case, if there are 2 elements, there are 4 elements in the power set. Now you should here's an exercise for you, and if S is instead 0 1 2, what is the power set of this? Try to find this.